All right, so we're gonna go over chapters 11 and 12 and how to do some of the problems from those two sections. All right, so here we go. Sharing screen, and we'll be off and running. Okay. So we have chapter 11 is all about two different kinds of a hypothesis tests. The one is for goodness of fit. And so does the sample fit the expected distribution well enough, basically is what it's trying to do. And then the second test is a test of independence, if two things are independent or not. And they both use this thing called the chi-square distribution. So we're going to be all about using that on our calculators today. All right. So is there a baby season, or does every season have the same number of babies born each year? The table below shows the number of babies from 964 that were looked at that were born in each season. Complete the rest of the table by filling in the expected frequencies. All right, so if it didn't matter what season the baby was born in, there would be 1/4 of the babies born in each season. So to find out this expected frequency, I'm just going to do 0.25 times 964. Or you could have just done 964 divided by 4. All right, so it appears as if these should have an expected frequency of 241 each time. So I just put 241 in for each one, and there you have it. So I think 2 behaves the same way. I think 3 is a little bit different. So Estelle, unless you stop me, I'm just going to roll through.
Really fast. Where did you get the 0.25?
So you have 4 different seasons, right?
Okay. Yeah.
We're
Okay.
expecting. So that, like I said, you could have done this as well. You could have just done 964, whoops, divided by 4.
Okay.
So each season would have 241.
Thank you.
Okay. A sample of 1,812 Texas government employees were selected for a study on race. The table below shows the results of the survey. The racial distribution for the state of Texas is shown in the second column above. Fill in the expected frequencies. All right, so basically what we're doing, we have 1,812 employees were selected. We're expecting 39% of them to be white. So we're going to do 0.39 times the 1,812 employees. And we're going to round these to the nearest whole number because we're talking about people. So the expected frequency for these people, we expect 707 government employees to be white of those 1,812. 41% to be Hispanic, so I'm going to do 0.41 times 1,812. And I get 743. So 743 is what we're expecting. Up there is the observed, the 725, 815, 163, 109. And then 9% are black, so 0.09 times 1,812. So we're expecting that number to be 163, right on the money. And then others, 11% of 1,812. And we get 199 for that one. So, oh, I didn't mean to do number 2, but there you go. I did both of them. And then we hit the button, and there you have it. All right, so they give you the percent, you just multiply that by the number, the sample, and that was what we'd expect. The next one, we're actually going to test and see if the observed frequency fits well with the expected frequency, the goodness of fit test. All right, so number 3, a die is rolled 120 times to see if it is fair. The table below shows the frequencies for each of the 6 possible outcomes. Complete the rest of the table by filling in the expected frequencies. Entering your answers in fraction. We're not going to need fractions. So we roll 120 times. And we're saying there's probably an equal probability of each roll of the die. So we're going to divide by 6 So if we roll 120 times, we're gonna expect to see each number 20 times. So 21s, 22s, 23s, 24s, 25s, and 26s. Okay, so this is a goodness of fit test, because we're seeing how what we observed fits well with the expected frequency. If it doesn't fit well, we're going to conclude the dice aren't fair. Okay, so correct statistical test to use, goodness of fit. What are the null and alternative hypothesis? This has to do with distribution. Okay, the goodness of fit test has to do with a distribution. So definitely not dependent or independent. We're going to deal with that later. But the distribution of die rolls is uniform is the null hypothesis, age 0. And then not uniform is going to be the alternative hypothesis. An alternative is always the opposite of the null. So let's make sure we got all those right so far. Okay, we're looking good. Now comes the tricky part. Some of us have calculators that have this test right here. Like this new calculator that I just downloaded has the chi-square GOF test. All right. If your calculator doesn't, then we're going to have to use this action right here. The test statistic is going to equal, let me make sure I get this right, the sum of the observed value minus the expected value squared over the expected value. All right, that's how we're going to calculate the test stat if you don't have a chi-square GOF test. So I'm going to show you the chi-square GOF is under stat test, and it's up right there, chi-square GOF test. All right, if you don't have that, there's a workaround. They didn't put the chi-square GOF test in the calculators until like the second or third generation TI-84. So some of them may not have it. See, the 84s probably all have it. It's the 83s that probably don't. So what I have to do to calculate this test stat is I have to calculate the observed value minus the expected value and then square it. So if I do observed minus expected for the first one, 19 minus 20, and then squared over the expected value, which was 20. And then this means sum, remember, and I have to add that to 19 minus 20 squared over 20 again. And then I got to add to that 32 minus 20 squared over 20. And then 19 minus 20 squared over 20. So it is a kind of a painstaking process doing it this way. But luckily, there's only a few of these on this assignment. And at max, only one on the final. So let's calculate those. I'm going to kind of do these in my head because I don't feel like typing all that in there. So here we go. 19 minus 20 is -1. -1 squared is +1. So I'm going to get 1/20 plus, same thing with 19 minus 20 is -1. -1 squared is +1. So 1/20 plus 32 minus 20 is 12. 12 squared is 144. So 144 20ths. And then 19 minus 20 squared over 20 again is 1/20 again. And none of these should be negative because you're squaring the numerator. When you square a number, it's always positive. So none of these are negative. So if you put negative numbers in, you didn't do it right. And then 10 minus 20 is -10. -10 squared is 100. So I calculate all that, hit enter, and that's my test statistic. That's my right here. That's this one is 12.4. Now the degrees of freedom shows what the shape of the curve is going to look like on the chi-square distribution. we have 6 different possibilities for my outcome here. So my degrees of freedom is always 1 less than the number of outcomes you can get. So my degrees of freedom here is going to be 5. Now the p-value, and this is for those of us that don't have the chi-square GOF test, but the p-value, you're going to go back to the distribution menu from back in the day, and we want chi-square CDF, and that's chi-square CDF right there. Hit enter. It asks you for a lower bound. The lower bound is always the test statistic. So 12.4. The upper bound is infinity. So we go 1 second EE 99. My degrees of freedom was 5. And paste. And there we go. We got 0.0297 is my p-value, 0.0297. So that's pretty low p-value. The level of significance that we wanted to deal with here is 0.01. That's a really low level of significance. Turns out 0.0297 is greater than 0.01. And since the p is greater than the alpha, we fail to reject the null hypothesis. As always, last few weeks, that's the going theme. So there's not sufficient evidence to conclude that the distribution of die-rolls is not uniform. Gonna be that one right there. Anytime the p-value is greater than alpha, insufficient evidence. All right, that's what you're looking for. So it's got to be one of the last two. Goodness of fit is all about the distribution, so it's the 4th one. And there we go. Excellent. We got it all right. Okay, so that's for everyone that doesn't have that test on their calculator. And I think that's the way Wendy does it in her video too. But the 84s all have this on our calculator. So let's do one where we can use the chi-square. Let's do number 5. So number 5. A recent national report states the marital status distribution of the male population age 18 or older is as follows. Never married 31.7%, married 56%, widowed 2.3%, divorced 10%. Table below shows the results of a random sample of 1,748 adult men from California. Test the claim that the distribution from California is as expected at the 5% significance level. All right. So what we got to do here is we got to take all these percentages and multiply it by the number of people in the sample. So for never married, 0.317 times 1748. So never married, we're expecting 554. So 579 is not that far off. 56% married, so 56 times 1748. We get 979. That's real close. Widowed, 2.3% are widowed, so 0.023 times 1748. We get 40 are widowed, real close to the 39 that we saw, and divorce 155. So 10% of 1748. That's going to be 175. 175. So let's make sure it takes. I hit the enter button and it takes. Correct statistical test to use is goodness of fit again. Does the data fit what was expected? All right, goodness of fit. So distribution of marital status in California is the same as it is nationally. All right, the null hypothesis is always the positive. It's not going to have a not or greater than or not equals to. It's always a positive. Distribution of marital status in California is the same as it is nationally. And distribution of marital status in California is not the same as it is nationally, is the alternative. Degrees of freedom, you have 4 categories. Degrees of freedom, 3. Okay. Now we're gonna go to the test statistic. This time we're gonna use the other method to do this. We're gonna use the chi-squared GOF test. To do that, I gotta put my two columns here into the table, and you all know how to enter these columns into a table. So stat, edit, and put those in there. 579, 975, 39, and 155. Then I go over to the second column, 554, 979, 40, and 175. So now those two columns are in a table. So now when I call up that chi-squared GOF test, it's going to ask me what my lists to use are, just like we've been doing. So stat, tests, up to chi-square GOF test, enter. My observed is L1. Yep, that was what I observed. My expected is an L2. That's good. My degrees of freedom was 3. So I got to switch that. Then I'm just going to go down to calculate. And then I have my test statistic is that 3.455. 3.455. My p-value is going to be 0.3266. Do those take? Very good. So the p-value is definitely greater than alpha, because alpha is what, 5%, 0.05, right? P-value is definitely greater than alpha. We expected that. I mean, look how close the data is to expected frequency. I mean, none of them are that far off, right? It'd have to be way far off in order for us to reject the null hypothesis. So we fail to reject again. So there's insufficient evidence to conclude that the distribution in California is not the same as it is nationally. I know that's a double negative, but there you have it. That's the way those work. Okie dokie. All right. I got two more to go do in this section. All right, so let's take a look at number 7. Number 6 works the same way as 5. Yeah, number 7. The data below shows sport preference and age of participant from a random sample of members of a sports club. Is there evidence to suggest that they are related? So what do people enjoy doing for exercise, right? So the frequencies of each age group and what they play. Are they dependent? Age and what they play. Are those two traits dependent? Are they related to one another? Or does it not even matter what age they are versus what they play? Okay, so it's a test of independence. So age and sport preference are independent, is going to be the null hypothesis. The null hypothesis is always going to have the word independent. And then the age and sports preference are dependent would be the alternative hypothesis. All right, let's anchor that in. Okay, very good. Okay, now this one we have not done what you're about to see yet. This thing is called a matrix. All right, what you see up here. And basically a matrix is a table of numbers. It's a table of numbers. You got rows. My pen is being stinky. You got rows going this way and columns going up and down. And we name a matrix by the number of rows, by the number of columns. Our matrix here has 1, 2, 3, 4 rows, and it has 3 columns. So we say its dimensions are 4 by 3. Put rows first and then columns second. So that's all you need to know for this. And then you go to the matrix option, which is above the x to the -1 button. So I go second matrix, and I want to edit matrix A. We're going to edit matrix A, and we're going to put those values in to matrix A. So we go over to edit, and edit matrix A every single time, and then the test we do is going to be easy. All right, so enter. I got a 4x3, so 4x3. Enter, and then there you see it. Now I just enter the numbers. So 84, 81, 81 in the first row. Second row, 109, 78, 64. Third row, 87, 90, and 59. Fourth row, 62, 79, and 30. So there I have my matrix entered. The 18 to 25 and the tennis swimming doesn't matter. That's all the calculations they're going to do now are going to give you whether or not they're dependent on one another, the columns and the rows. Okay, so here we go. The test we use, we go to stat, tests, and this time we're going to just use the plain chi-square test. All right, so we use the chi-square test, enter, and it tells you the observed matrix, and the calculator actually calculates the expected matrix for you. So you don't have to calculate the expected matrix, thankfully. It does it for you. And we can see what that looks like in a minute. So then we go down to calculate, and there we go. Our test statistic is 20.02. And then our p-val 20.022. That's right. I got to enter it to 3 decimal places. Then our p-value is very small. So that stands to reason we're going to reject the null hypothesis. And age and what people play are definitely dependent variables. Okay, so p-value, my significance level is 0.01. Definitely less than 0.01. 0.0027 is less than 0.01. Therefore, we reject the null. P less than alpha, reject the null. Okay, now this one's all about dependent and independent. P is less than alpha, we have sufficient evidence, that means. So it's got to be the first, second, or third. Okay, it can't be the third one because we're not talking about distribution being the same or not the same. We're talking about whether two variables are dependent or independent. So there is sufficient evidence to conclude that age and sport are dependent then. And there we go, chi-square test for independence. Submit question. Money. All right. I think I'm going to do one more of those. So number 9 works the same way. Estelle, are we good?
Doing good.
Excellent. All right. Let's take a look at number 9 too. So number 9, a researcher is interested in investigating whether living situation and pet ownership are dependent. The table below shows the results of a survey. So we got dog houses, cat houses, various other pets, and then no pets. So single people, what do they have for pets? Family, what do they have? And couples, what do they have? So is the living situation and what pets they own, are they dependent on one another? So we want an independence test. Pet ownership and living situation are independent, is going to be the null. And then the alternative is going to be that they are dependent. So boom, are dependent. All right, now we go back in. Oh, we forgot to look at this matrix. So you could go down to names, and if you hit enter, it's going to show you that matrix. So those are the expected values if they were independent variables. That's what we'd expect to get. All right, and then you're probably going to see that the other ones are pretty far off from those. Right, let's see the other ones. Where are they? Right here. So the over 40 crowd, we expected 65% to be involved in tennis, 62% is way under 79 for swimming. And then we expected 44% to play basketball, and only 30% did. So they're far off. Alrighty, so the calculator calculates that for you, thankfully. So, but let's put it on our new matrix and see what we get. So we're down here with the pets. So second matrix again. Just edit matrix A. So keep it right there. Go over to edit, hit enter. It's 4x3 again. I don't even have to change that part. Now I go down here and I could just change my numbers. So 57, 95, 99, 113, 90, 92, 34, 42, 52, 65, 56, and 60. So there are my matrix values for this situation. Looks like some of them didn't get entered properly. That one should be 34. And then that one should be 52. Because you get one of these numbers wrong, it's going to booger up all the calculations. So that looks good. All right. Now I go to stat, tests. Going to go up to chi-square, enter. Yep, observed is A, expected is B. We don't have to change that at all once you change the matrix. Okay, so then we go down to calculate, enter. So our chi-square value is going to be our test statistics, 19.065. Our p-value is 0.0041. Looks like these are we're gonna assume these are dependent too. So the p-value at a 5% significance level is definitely less than. When it's less than, we reject the null. So we do have sufficient evidence to conclude something. And that we're accepting the alternative hypothesis that pet ownership and living situation are dependent. So it's that one there. Enter, and we got it. All righty. So single person. All right. So they're dependent on one another. So that is section 11, chapter 11 in a nutshell. Now we're going to go off to chapter 12. Chapter 12, if you've all had Math 111 before, chapter 12 may look, you may have done it before. This stuff from chapter 12. It's all about linear regression. So we are going to calculate what's called correlation coefficients, and we're going to calculate lines of best fit in this section. And we're going to use the lines of best fit to predict values. First of all, correlation coefficient. If we have data that when I plot the data, looks like, you know, scattered like that, R is pretty close to 1 here, right? R is close to 1. The closer it is to a line with a positive slope, the closer the correlation coefficient is going to be to 1. R stands for correlation coefficient. If you go on down like this, the slope is negative. R is close to -1. And then if you just have data that's all over the place, like you don't have any rhyme or reason behind what the data is, R is close to 0. Okay, so R is always between -1 and +1. If it's exactly aligned, if the data lines up perfectly, R is going to be -1 or +1. All righty. So your calculator has capabilities of calculating this correlation coefficient. So let's go over how to do that. Because you definitely don't want to be doing this by hand. The formulas are really cumbersome. Okay. First things first, you got to do this thing called turning diagnostics on, because the diagnostics are what are going to give you the R value. So we got to look for the catalog button on our calculator. and it's right above 0. So if I go second catalog, now I'm going to scroll down until I see a line that says diagnostics on. If you don't have diagnostics on, you will not see your R value. As you can see, every single function on the calculator is in this catalog. So you see the chi-square test and the chi-square GOF test that we just used. So we go down to find diagnostics. Here we go, diagnostics on. That's what you want, diagnostic on. And that tells the calculator you want to see the R value. Enter and hit enter one more time. And now it's on. All right, now what we're going to do, we got to enter this table. Well, this table is going to be entered via stat edit, just like we've done 100 times already. So stat edit, you got stuff in there like I do, go up and clear enter on the list. Clear enter. Now I just start entering those numbers. So 29, 42, 58, 50, 35, 31, 11. For some reason it doesn't, I must have gone too fast sometimes when I type my numbers. 31, 11, 50, and 12. So there is list 1. List 2, 114, 19, 109, 163, negative 63, negative. I did I type 2 negatives? 114, 19, 109, 163. Next one's negative 63. Oh, I bet you I know what. I got to use my negative button on my calculator. I use the negative button on my computer and it doesn't like that. So negative 63, negative 52. So I actually got to move my mouse and hit the buttons now, which is slower. Then 138, negative 15. So I got my 2 sets of data in there. Now I got to figure out if they're related. How related are they linearly? Okay, so to find out the linear relation, I'm going to go to stat and I'm going to go to calc this time. Stat, calc, you're going to go down to LINREG. That means linear regression. So they're going to give you an A value, which is going to be the slope of the line of best fit. They're going to give you a B value, which is the y-intercept of the line of best fit. And then they're going to give you your correlation coefficient. Enter X list L1, Y list L2, frequency list, don't need to. Store reg EQ if you want to see, we don't need to do that. Then calculate. And there we go. So our slope is 3.74. Our B value is negative 92.27. R squared is just, that's what the calculation does. It's kind of like the standard deviation. They do this, when you calculate that by hand, you come up with that sigma squared. Then you got to square root it to find the standard deviation. Same thing here. The calculation involves R squared, and you'd have to square root that to find the actual R. So it's 0.6802 to 4 decimal places. There we go. So the rest of the problem we're going to do, it looks like we're going to do 4 more. Let's take a look at number 2. So this time they give you the results of this analysis, and as you can see, what they have right here is kind of looks the same as what my calculator has on it. So basically what that means then is that the line of best fit on this is going to be y equals the slope negative 1.183x plus the y-intercept 39.5. So this is used to predict the number of sit-ups a person who watches 11 hours of TV can do. You gotta think not many, but we'll see what happens. So what I'm gonna do to calculate that is I'm actually gonna put 11 in for that X right there. I'm gonna put 11 in for that X. So we're just gonna do that on our calculator. So negative 1.183 times 11 plus 39.5. And they want a nearest whole number here because it's sit-ups. Even though I think you can do a half a sit-up, I think I've done plenty of those. So 26. So you basically just use that formula for prediction. And you watching 11 hours of TV, I doubt you're doing 26 sit-ups, but there it is. All right, let's take a look at 4, because 3 is the same thing. 3 is the same exact problem. They just want you to plug it into the formula. Number 4, the following is data for the first and second quiz scores for 8 students in a class. Now, My Open Math has you can plot points on it. So it wants you to plot the points and then sketch a line that best fits the data. So here we go. I'm gonna pick the point plotter tool over here. It's this big black dot all the way at the end. That's gonna allow me to plot points. So first things first, I'm gonna plot the point 17, 17. So 17, 17 is about right there. My Open Math gives you some grace on this too, so you may not get it right on the money, but they give you a little bit of leeway. 19, 17 is right there, and 21, 19, about right there. 23, 20, gonna be on the line, a little bit left of 24. 25, 22, halfway up, a little past 24. 26, 25, a little bit above 24. 28, 24. Oh, finally, we got one right on the crosshairs. And then 30, 29, just above there, 30, 29. All right, that's looking pretty linear to me. But what we're going to do now is we're going to kind of try to draw a line of best fit. So I picked the line figure. My line is going to go like right through the middle of those points, right through the middle of those points. So let's visualize it, and then I'm going to click. Let's click it right there, and then I'm going to drag it up, and I'm going to click it somewhere else. So like half the points are above the graph, half the points are below the graph. I'm going to click again, and then we're going to use that to predict the value of the second score if the student had a first score of 24. So student had a first score of 24, that's right here. What's the second score going to be? The prediction according to the line is about 22, right? The x-axis represents quiz 1, y-axis quiz 2. So I go over to 24 on quiz 1. Quiz 2 is about at 22. So that's going to be my guess right here. Hopefully all has gone well with all this. Hit enter. You liked it. Liked it all. Okay, so plot the points. Get the line in there and use that line to predict. All righty. Fun little problem. Okay, let's look at 5. Statistics students in Oxnard College sampled 11 textbooks in the Condor bookstore and recorded the number of pages in each textbook and its cost. This must be an old table, because ain't no way books are going to cost that little. Now they cost nothing because they're all online, which is nice. Okay, so I got to put these tables into my stat edit. I'm going to put those in. So clear, enter on that one. Go up here. We're going to do clear, enter on that one. And I'm going to put these values in. So 756, 264. Went too fast. 264. 624. 649. 385. 850. 806. 884. 594. 862. And 880. So that's my number of pages in each book. And I go over in the cost, $64.92, etc. Just put them into your table. This should be old hat now. Kind of amazing how much technology is in this calculator. To be able to do all this stuff. So I'm entering all those in. Hopefully I entered them all in correctly, because if I made one mistake, it's going to throw the whole deal off. So hopefully it's good. All right. So there are my two lists. Put them in there. Now I got to find my y equals mx plus b. So I just go stat, calc, down the line reg, enter. Yes, X list is L1, Y list is L2, frequency, we don't have a frequency list. Frequency, the regression equation, I don't need to store that anywhere, I'm not looking at it. And calculate. So there we have it, I got, and it wants 2 decimal places. So 0.07 to the nearest 2 decimal places for the slope. And for the y-intercept, it was 19.64. Now we want to figure out what the cost is when the number of pages is 757. So all you're doing is you're plugging 757 in for X. So 0.07 times 757 plus 19.64. So I'm suspecting a cost of $72.63 for a book that has 757 pages. And we got them all. Great problem. I'm pretty sure there's one like that on the final. Okay, let's do last one. And the last one, basically, you're just using the equation to predict. So it says the table below shows the number of state registered automatic weapons and the murder rate for several Northwestern states. I didn't know there was that many states in the Northwest, 8 states, but there you go. So we have that many thousands of automatic weapons, and then we got number of murders per 100,000 residents. So this data can be modeled by the equation y equals 0.85x plus 4.01. Use this equation to answer the following. Special note, I suggest you verify this equation by, well, we could do that, but you know, we've done it a few times, so let's just go. How many murders per 100,000 residents can be expected in a state with 5.3 thousand automatic weapons? So all I'm going to do is I'm going to do 0.85 times 5.3 plus where is it, 4.01. So we're going to expect 8.515 murders per 100,000 residents if that community has that many weapons. All right. Then I'm going to put 3.5 in for X. So 0.85 times 3.5 plus 4.01. And I get 6.985. So 6.985 murders per 100,000 residents if there's that many weapons in the community. And there you have it. That's the some select problems. I mean, the ones I didn't go over were pretty much like the ones I did go over. So we should be able to use those to take care of it. All righty. That's it.